Okay, let's get started here because we want to prepare as much as we can prior to the test on Wednesday, right? So we got that test on Wednesday coming up. Uh, so y'all did very good on finishing the homeworks, and I don't know why some of those are black and some are blue, but there was a homework due last night. But now, now most people did this, but if you didn't start that or didn't finish as much as you wanted for that one, remember you still have this grace period, right? So you still have today and tomorrow. You can work on that, okay, and still earn points, but not 100% of the new points, right? But you can still earn points on that to improve your score. So especially if you haven't started that, it would be beneficial to work on that, okay? Now, we have this quiz on these two homeworks that is right now posted for due this evening, but I'm going to delay that. I will set that back to the time of the exam. So that will be due at 11:30 on Wednesday, 11:30 on Wednesday. So you have a little bit of extra time. And then this homework I'm going to postpone slightly, okay, because we're just talking about that today. But I want you to be thinking about preparing for the test and not worrying so much about this homework, okay? And by preparing for the test, I mean reviewing your prior homeworks, and then also don't forget the sample test, right? Okay, which is on the Blackboard page, and so you know the location, right? It's down here on the Blackboard page under that sample test link, and the answers are posted, all right? So I have posted the answers as of this morning. So those are there along with the sample test. But as I keep cautioning you, right, you want to do the sample test first, right, before looking at the answers. Now, since we're just slightly behind on that last homework, that section 1.4.1, that's all about linear functions, straight lines, and so and there are a lot of questions on the sample test that are about straight lines. So I have circled those well, that should be red, but does it look red? A little bit. So I've circled those questions in red, and that pertain to linear functions here on the sample test. So I will not include questions like that on the test. We're going to talk about those today, though, and we're going to go through some of these questions after the lecture, okay, as kind of a follow-up to the lecture, all right? But I will not include those on the exam, so you're not responsible for those. And those are all part of that 1.41 homework, the due date of which I will postpone, right? Okay? So the big thing there, the big takeaway is that homework is postponed, and the quiz is delayed, right, until the time of the test. Not midnight, though, on Wednesday, the time of the test on Wednesday. And then these problems circled in red on the sample test, I think I got all of them, will not be on the test, okay? Now, that still leaves you a lot to review for the sample test, but not as much as before, okay, obviously. So, but again, we're going to look at some of these questions about straight lines, linear functions, after we do the lecture about linear functions today. All right, so are we all on, we all know where we're at here for Wednesday, okay? So it's basically through that 1.3 part 2 homework and that 1.3 quiz. That's the content of the test, okay? On Wednesday. So we reviewed a lot of that with that practice exam last time, and then of course you've got the sample test, right, to work on. Okay, so any outstanding questions there that you guys want to ask before we crank up here and get too far into this? Okay. All right. Let's switch back to the just as a little warm up here. Let's switch back to the notes and just answer. I had one example from these notes that we didn't talk about, so I will use this as just a warm up today. All right. So here's the question. I've got it here written into the notes. All right. So here's the question, and it's solving an equation. So we want to solve this equation, fx equals to 1. Now, we're referring to this function in this graph, number 41, okay? So looking at that graph, I want you to solve that equation, fx equals 1. And then in 43, same sort of question, I want you to solve this equation, fx equals 0, f of x, I should say, right? Okay? And here, f of x equals 1, all right, for this pertains to number 43, right? Now, think about, you're not used to seeing equations expressed like this, but this is an equation. It's got an equal mark in it, right? So it's definitely an equation, right? And it has an unknown in it. The unknown is x. F is not the unknown. F is this function, and you know what this function is because you've got a graph of this function, right? Okay, so this is not an unknown, but x is the unknown here, right? And that's how equations work, right? Equations have unknowns in them, and then you want to find the value of the unknown, right, that will make the equation true. So that's exactly what's happening in this particular statement, right? Okay, we have this unknown. We want to find the value for x that will make this equation true, right? Okay, so think about that's what's that asking you, right? Okay, if you say that in a little bit more expressive form, you would say, oh, I want to find these values for x, right, such that f of x is equal to 1. But you have to use the graph to do that because that's all you know about the function f, all right? Okay, so try that for 41 there, and then this equation, try that for 43. You might have to give estimates now, okay, because you're looking at graphs, right, okay? And sometimes from graphs you have to give estimates. That's one of the disadvantages to graphs, right? It's not always possible to be perfectly accurate, but you just want to give it your best estimate, right, okay, from what you can see there, right? So in 41, what x makes f of x equal 1? 43, what x makes f of x equal 0? Make sure you write down all the solutions, okay? Remember, when you're solving equations, usually, not always, but most of the time, you want to write down all possible solutions to an equation. So if there's more than one, write them all down, okay? So where does f of x equal 1? There's a question like this one on the sample test, so you'll notice it when you come to it. It's pretty early in the sample test. So try to get some estimate down. I'm going to ask someone to give their estimate and share their logic for that. I think I've run through all the cards, so everyone is eligible again. I love that. Putting everyone ill at ease again now, because that fear is conducive to learning. No. Can't leave yet, all right? Okay. All right, I'm going to ask someone here. So let's call someone just for 41, okay? So solve that equation. Emiliano, you're the... Uh, 2 point what? 2.98, okay? So you're saying you think x is approximately 2.98, and that's your only solution there? Oh, a negative, okay. So also negative what? Same thing? Oh, 2.98. Okay. All right. So how can we, when you're solving an equation, right? One of the nice things about equations is that you can check your answer, right? Okay. So how can we check the answer when we solve an equation? Well, we take our solution correct and we plug it back into the equation, right? Okay. So let's take this. Let's take one of Emiliano's solutions here, and let's plug it back into the equation for x. So I'm going to try the positive one. So I'm going to write f of 2.98 equals 1, right? Okay, and how do we check, Emiliano, if that's true? Oh, yeah. Well, you're saying how you got the 2.98, okay? Right, okay? But I'm just asking, how can we check this? I'm asking a slightly different question here. So how can we check if you did this right? So how can we check if f of 2.98 really does equal 1? That is an equation, okay? Yeah, that's it, right? Yeah, that's it. That's the equation. That's right. Okay, but there's more here, Nadine, right? Because remember, there's the graph, right? Okay, so the graph is wrapped up into this situation as well. So using the graph, you're usually thinking of plugging this number into a formula, but we're going to plug this number into a graph, okay, to check if this equation is true. So how do we do that? All right. So I'm just asking you, how do you evaluate f of 2.98 using the graph, right? What do? You find 2.98 here, right? Okay. On the x-axis, 2.98 is about right there, right? Okay. And Emiliani was so precise, it's hard to know exactly where the 2.98 is, but somewhere right there, okay, right? And then go up, and what do we hit there? 1, yeah, okay, so, I think that's, I think that checks, right? Okay, so some of you might have had slightly different answers than 2.98, right? Okay, but it's somewhere here close to 3, right? Okay, that's the x value, so that when you plug it into the formula, you'll get a matching output of 1. And the same thing happens here over on the left-hand side, right? If you try f of minus 2.98, right, you will also get as your matching output 1, okay? So Emiliano solved that equation perfectly. But now, Emiliano, when you solved it, right, you weren't just guessing, right? How did you actually decide that it was 2.98? Okay, so this is what you were trying to tell me earlier. Okay, how did you arrive at the number, at the solution 2.98? Okay, that's what you were explaining to me earlier. What? No, I don't think that's not what you said earlier, right? You said I knew I wanted my y value to be what? 1, right? Okay. So you started at 1 on the y-axis, and then what? Yeah, you drew a line across, right? Okay, so you sort of drew this box backwards, right? Okay, you started at 1 and then came across till you hit the graph, right, on either side, and then you went down and you read off the x value, right? Okay, and that's how you got the 2.98. Yeah, that's exactly what you want to do, right? Okay, so you see, Nadine, there's how you can use a graph to solve an equation, okay? All right. Still an equation that we're solving, okay? All right, so now y'all can do this one easy, right? Okay, here's one we like to solve a lot. F of x equals 0, okay? That's an equation that comes up quite frequently, all right? So let's see if we can use 43 to solve this equation. And again, you can give an estimate, right? Okay? So if you already wrote that one down, that's great. Just sit here for a second while your classmates catch up with you, okay? So if you don't get a perfect estimate right, if you're a little nearsighted like me and you're having trouble seeing that screen, that's fine. Okay, just give it your best shot there. Okay. Okay. All right. So I'm going to ask somebody else, right? Okay. So maybe somebody who's been up before. Leslie. All right, Leslie. Okay. All right. All right. So I put you on the spot here, but you can get you can consult here with your seatmates here. Okay, your row mates here about what x would be here, right? Okay. So what x gives us f of x equal 0? 1.4, okay? I think that's a good estimate, Leslie, okay? So I think that's maybe what I would have written down. X is 1.4, and there's another one, though, okay? What's the other one? Negative 1.4. Yeah, both of these graphs are symmetric, right? Very symmetric. They look the same on the left and the right. Well, they're just mirror images of each other on the left and the right, okay? So since 1.4 there is a solution to this equation, then so is minus 1.4, right? Okay, so we can check that easily, right? Okay, by just going to 1.4 on the x-axis or minus 1.4 on the x-axis, right? And then we go up and down until we hit the curve, but you don't have to go anywhere, right? Okay, because the curve is already right there, right, at 1.4. So that means the matching output is 0, okay? So you did that exactly right, okay? Solving this equation is the same as looking for where the graph crosses the x-axis. Those numbers are called x-intercepts, all right? So what we found here are the x-intercepts for this graph, where that graph crosses the x-axis. So you have one x-intercept on the right and then another x-intercept on the left, okay? Up here this is the y-intercept where it crosses where the graph crosses the y-axis, okay? You can find the y-intercept in kind of an opposite manner by solving this equation. That's an easy equation to solve, though, okay? Because all you have to do here is to solve this equation is just evaluate f of 0, right? Okay, so go and find 0 on the x-axis, and here you have to come up to the curve, and of course you get 2, right? So the y-intercept here is 2, okay? So notice that subtle difference there. Right? When I set f of x to 0 and solve that equation, you're going to find where the graph crosses the x-axis. Those are called x-intercepts. On the other hand, if you substitute 0 for x, right, you're going to find the y-intercept, where the graph crosses the y-axis. And those are usually numbers that we're interested in, okay, because they often have lots of applications. We may get a chance to see some applications of x and y-intercepts today when we're talking about straight lines, okay. All right, so there's our little warm-up, all right, of slight review there of what we talked about last time. Okay, now I'm going to switch notes here, so we're going on to a new set of notes, and we're going to talk about the most important type of function. So we've just been talking about functions in general so far, and you know, how functions work. But now we're going to narrow our focus a little bit to a particular type of function. And this is a type of function that is applied most frequently in practice because it's the easiest to work with. It's the easiest to understand, okay? And this type of function is called a linear function. And when you graph a linear function, of course, you get a straight line, okay? So here we're going to be talking about straight lines or linear functions. So I'm going to show you there, we're going to see lots of applications of linear functions. because again, they're come up frequently in practice, and they're really important also in calculus, but in kind of an unusual way, all right, in calculus. For those of y'all that are science majors that are going to take calculus. All right, so I want to show you the three basic fundamental properties of linear functions, and really everything that we do when we're studying linear functions or using linear functions in applications is really going to revolve around these three properties. So it's really important that you sort of commit these to memory, okay, or practice with them enough that you'll learn them, memorize them. All right, so the first property is how linear functions look like when they're expressed as formulas, okay? So when you express a linear function as a formula, you get a very simple formula. So that's one of the things that's nice about linear functions, okay? And the formula for a linear function can always be written in this format, all right? Where x is the input variable now, okay? M here is just a constant, and this value b is also just a constant, all right? So very little, very simple formula for linear functions. You just have a number times x plus, or this could be minus, right? Because this value could be negative, plus or minus a second value, okay? So a really simple formula for linear functions. And again, that makes them easy to understand and use, right? Because their formulas are not super complicated, okay? Now, I want to caution you a little bit. You have to read this carefully, okay? It says, the formula for a linear function can be written in this format, but we won't always encounter linear functions written in this format, okay? So sometimes we'll see linear functions where their formulas are written in a different style, okay? All right, but that doesn't keep them from being linear functions. But if you can take the formula and simplify it to this format, then it's a linear function, okay? All right, so that first property just tells you what the formulas for linear functions look like, right? Now, we don't always, though, express functions as formulas. We sometimes express them as graphs, right, as we just saw in that warm-up exercise, okay? Well, when you write or when you express linear functions as a graph, you get, of course, a straight line, okay? That's why linear functions are called linear, all right? So when you graph a linear function, you always get a straight line. So when you graph a formula like this, right, okay, a simple formula like this, you're always going to get, from the graph, you're always going to get a straight line, okay? So that's nice because, of course, straight lines are very simple graphs, right? So it's very easy for us to graph linear functions. So easy, in fact, that we can do that by hand very easily, right, without having to rely on a calculator or a computer. And we can also visualize the graph of a linear function. We can also visualize the graph of a linear function pretty easily without even having to draw it, okay? We can visualize it in our mind because, again, the graph is so simple, okay? All right, now, so those are pretty straightforward properties. Now, the third property has to do with how linear functions appear in the third way that we like to write down functions. So we like to express functions as what? Formulas. Okay, and graphs, and what's the other way? No, equations would be a formula, okay, right? What? Table, right, okay. So the third important way for expressing functions is tables. And this third property sort of applies to how a linear function would look if it was written as a table, okay? All right, so now this one's a little bit more complicated, though, all right? So we have to think about this a little bit. So this third property says, in a linear function, when the input, typically x, right? When the input increases by a steady amount, the output will change also by a steady amount. It doesn't have to be the same steady amount, okay? All right, but as long as when the input goes up by a steady amount, the output also changes by a steady amount, then you know you have a linear function. That's how linear functions always behave, okay? Now, the change in the y value can be positive or it can be negative, okay? Notice I didn't say increase, I just said changes. But notice the input is increasing here, right? So when the input goes up, when x goes up, if the y value changes steadily, okay, either up or down steadily, okay, then that is a linear function. So when you convert a linear function to a table, you're going to notice this property in the table, okay? When the input goes up by a steady amount, the output will change by a steady amount, okay? All right, now, that property leads to an important definition, a really important definition that's really fundamental to linear functions, okay? So that's this bottom line here, all right? When you increase x by 1 unit, all right, I don't know how x is measured, but when you increase x by 1, all right, then the change in the y value, the change in the output, when you increase x by 1, that is called the slope or the rate of change for the line, okay? And that turns out to be a really crucial number for working with lines, okay? So again, the amount that the y changes could be positive or negative, but the amount that the y changes when x goes up by 1, exactly 1, okay, that number is called the slope, or sometimes the rate of change of the linear function. Makes sense, right? Well, the term rate of change certainly makes sense, right? Slope's a little bit more obscure why we use that term, okay? But I think that will become more clear how the word slope comes about when we work with some more examples of linear functions, right? So really, those are the 3 ways of recognizing linear functions. If it's a formula, you know what the formula is going to look like, right? It's a very simple formula. Y equals mx plus b, okay? Graph, of course, is a straight line, right? Okay, so if you're looking at the graph of a straight line, you know that's a linear function. And then finally, when the x increases by a steady amount, if the y also changes by a steady amount, positive or negative, but changes by a steady amount, then that is a linear function. Okay, that also is going to be a linear function. All right, let's see if we can remember those properties now. Okay, with just some very simple exercises here. All right. So again, we won't have questions like this on the test, unfortunately, because these are really give-me questions. So this would really be a way of padding your score on the test. But you'll have to wait till test number 2. All right. So here's a question. I've written down a bunch of function formulas, and I just want to know which of these are linear functions. Okay. So we're not going to graph them to check which are linear functions. We just want to see, can the formula be written in this format? If the formula can be written in this format, then we know we have a linear function. All right. So what about A there? Is that a linear function? Sure, right. That's pretty obvious, right? Okay. That one fits just exactly right into that format. Okay. The M value here is 3, right? And the B value is minus 5. Okay. All right, so that's definitely a linear function. So if you graph 3x minus 5, you are going to see a straight line. Okay, so I'm not going to graph that right now, but if we graph that, the graph would turn out to be a straight line. And since straight lines are very simple curves, right? Okay, what can be simpler than a straight line? Then these are easy to graph by hand. So we will expect. I will expect you to be able to graph linear functions by hand. Many functions we won't graph by hand, but linear functions we will. Okay. All right. I want to show you, before we move on to the next example, though, I want to show you something about the value b. Okay, because that has a geometric significance to us. So, and it's easy to understand. So I'm going to show that to you. If we take 0 and use that as our input, right, for this function. Well, let me do that off to the side. Okay. So if I take 0 and use that as input to this function f, right? Okay. Notice what I get here is what? So if you plug 0 into this formula, what are you going to get as the matching output? -5. Yeah, right. Sure, you're going to get this value, right? Okay. You're going to get this value, correct? But on the graph, what does f of 0 correspond to? We just talked about this, right? What point on the graph is that called? That, not the x-intercept, close. That's the y-intercept, right? Okay. See, if you plug 0 in for x, right, where x is 0, that is the y-axis. So f of 0 is going to be where that graph crosses the y-axis. That is the y-intercept. Aha! So guess what? This value b in your equation, that is always, for any linear function, that always is going to correspond to the y-intercept. Okay? So for any linear function, not just this one, but for any linear function, this value b in the formula is always always going to be the y-intercept, all right, where the graph crosses the y-axis. Notice that is very helpful already in helping you understand what the graph looks like, right? Okay, because you already know where, just by knowing that value for b, right, you'll know where the curve crosses the y-axis, and it's just a straight line, right? So that already gives you some powerful information about what the graph is going to look like. Okay, all right, let's try this one now. All right, so is that going to be a linear function? What do you think? So it is a function. When we graph it, we will get some sort of curve, but is it going to be linear? The answer here is no. Okay, all right. Not going to be linear, all right? There's no way to take that formula, there's no way to take this formula and put it into this format, okay? The thing that's messing you up here is the x in this denominator, all right, okay? That prevents this function from being a linear function, all right? By the way now, what would be, here's another way you can recognize this is not a linear function. What is going to be the domain for, in general, what's going to be the domain for linear functions? So what numbers will we be able to plug in for x here and do this arithmetic? Remember, m is just a value and b is just a value, right? So what would be the domain for linear functions in general? Well, one input is going to equal one output, so it is a function, Furman, right? But domain, remember, what does domain mean? That means numbers, that the set of numbers you can plug in for x. So, Furman, what numbers can we plug in for x here in this formula? What? All real numbers, right? It's going to be all real numbers, right? Okay? It's going to be all real numbers. What situation are you trying to avoid, remember, when you're looking for the domain? With a formula, what two situations were we trying to avoid? You recall this from last time now? No decimals? No, decimals are fine, okay? Decimals, we like decimals, all right? Okay, all right. What do you have to be careful of when you have a function represented by a formula? What can you not do? No, I'm going to give you that you have a function formula, all right, okay? So I'll give you that you've got a function formula. But in looking for the domain from the formula, remember what two situations do we have to be careful of? One of them occurs here. No, fractions are okay. Well, what about fractions? I'm sorry, Kevin. What about fractions? Okay. All right. That part's not helping me. All right. All right. Yeah. What issue? Remember, domain means numbers you can substitute for x. Okay. So what issue may arise in this function formula when you're substituting a value for x? Negative. Well, yeah, you might get negatives, but negative numbers are they're not really an issue for us, okay? We're used to working with negative numbers. Sometimes they can be an issue for us, all right? But in general, no. Yeah, what, Nadine? There's more than one x, okay? Well, domain means the set of all numbers you can substitute for x, okay? All right, so this is a very important idea, okay, that I'm discussing now. So you've got to get this solidified in your mind before the test, or I could just, those test scores are just, it's a linear function going down, okay, like this, right? Okay, what was the issue right here that we were so careful about last time? See, domain means what numbers can we substitute for x. So in this function, why do we have to be careful about substituting certain values for x? If y'all are drifting off somewhere or playing with your cell phone, you've got to get your attention back on the class, or we'll just be making short work of your time in college algebra, okay? Hate to tell you this, that is going to put a serious crimp in the rest of your college plans, all right? That is just statistical fact, okay? All right, so what issue there in this equation, in this formula, might we run into when we're substituting values for x? Try some. Any problem with 0? If I try, for this formula, if I try plugging 0 in for x, any issue here? What do I get? You get minus 5 over 2. Perfectly good number, minus 5 over 2. Okay? Nothing wrong with minus 5 over 2. That's minus 2.5. Perfectly nice number. Occupies a spot on the real number line. Nothing wrong with it there. Okay? Let's try another one. Don't see any problems here either. F of 1, that would be what? Minus 2 over 3. So that's minus 2/3. Okay? That's all right. All right? What about my f of minus 1 here? I think that's going to be something like minus 8 over 1, which is negative 8, but nothing wrong. Did I do that right? I think so. Okay. So nothing wrong with negative 8. What happens with minus 2, though? Yeah, what, Emiliano? The fraction cancels out, okay? See if you, I think I know what you're saying, but you got to say that a little bit more precisely for me. The denominator is going to equal 0. Yeah, that's what I wanted to hear, right? Okay, the denominator there is going to turn out equaling 0, right? The numerator comes out as minus 11. That's no problem, but the denominator ends up being 0, okay? And what's wrong there? It's undefined. That's right, okay? It is undefined, all right? So remember, we spent a lot of time with examples like this last time, right? Okay? You cannot substitute values for x, right, that will cause your denominator to turn out to be 0, correct? Because you'll end up dividing by 0, right? Okay? So how did we avoid that situation? What did we do? When we had a formula like this one, what did we do? We took the denominator and what? Set it equal to 0, and then we solved that equation, correct? Okay, and we solved that equation, and then those numbers we threw out of the domain. Okay, those numbers we threw out of the domain. So when you take x plus 2 here, and set that to 0, and solve that, you get x equal minus 2. So that number cannot be in your domain for that function. All right, that number is not in the domain. Everything else is okay, but everything else is okay, including these values, but minus 2 not in the domain, right? So domain here would be all real numbers except minus 2. But for a linear function, you don't have a fraction like this, right? Okay, linear functions, you see, have very straightforward formulas, like mx plus b, correct? So you can plug in any number for x. You can do this arithmetic, right? This is just a multiplication. So you'd be able to do that multiplication, and then you would be able to add on the b, correct? That's just a simple addition. So for linear functions, you don't have this sort of issue occurring. So what would the domain for a linear function be? So here we have all real numbers except minus 2, right? But for a linear function, is there any issues? Will there be any issues with us doing the arithmetic here? Take this as an example. If you plug a number in for x, will you be able to carry out this arithmetic? Yeah, right, okay. You may need a calculator to help you. That's not the issue, all right? But with a calculator, you could multiply any number times 3. You could certainly subtract 5, right, from that product. So the domain for this function, and in fact for any linear function, will be all real numbers, okay? So if you end up with in general, it will be all real numbers. So if you end up with a function whose domain is not going to be all real numbers, like part B here, then chances are that's not going to be a linear function, okay? All right? Because that's not the issue, that don't have that problem occurring, right, for linear functions. By the way, here you can write all real numbers except minus 2. Sometimes the homework, I noticed this in the homework, sometimes the homework will say all real numbers, but then it will write something like x not equal to minus 2. That means except minus 2, right? But they use the not equal mark, which is the equal with a line through it, okay, to say except. So when you see that in the homework, or you may have already seen that in the homework, right? Okay, that's just another way of saying except. All right, let's look at C. Okay, so I see we're already having issues identifying formulas of linear functions, but we'll get better at it, okay? All right, what about, so A is a linear function, B is not, okay, because this x in the denominator just prevents this from being a linear function, okay? Not going to be a linear function. So when you graph this, when you graph 3x minus 5 over x plus 2, what sort of picture are you going to get? I have no idea, okay? You're going to get a curve, all right? But the curve is not going to be a straight line, okay? Not going to be a straight line, all right? So when you graph this thing, I don't know what sort of curve you're going to see, but you will not see a straight line, okay? Straight line graphs are reserved for linear functions. All right, what about now C? Is that going to be a linear function? Okay, Leslie says yes. All right. Leslie, if that's yes, can you put this into this form for me? It's not quite written in that form. So can you rewrite that in that form? What would it look like in the mx plus b form? Oh, so you're, all right, so negative 3x over 2 plus what? Plus 5 over 2, right, okay, that's correct. Or you could say minus 3 halves x, rather than minus 3x over 2 plus the 5 halves, okay? Right, there it is in mx plus b form. So this is the m value, right, and that is the b value, which we know, of course, is the y-intercept, all right? So the y-intercept for this linear function is 5 halves. That's where it's going to cross the y-axis. Right? So domain is all real numbers, right? Okay, domain is all real numbers. See that very simple formula. Doesn't matter what number you substitute for x, okay, you'll be able to carry out the arithmetic and get a real number as the result. What about D? Almost the same as C, right? Okay, so is that a linear function? There's no B, okay, but the B is kind of easy to manufacture because you could write 3/2 x as 3/2 x plus 0, you see, okay? 3/2 x plus 0 is the same as 3/2 x. So you can write it in the mx plus b form, okay? The b value would be 0, and the m value here, this first coefficient, would be 3/2, okay? So this just happens to have y-intercept 0, okay? But that is a linear function, right? That does count as a linear function. What about E? There's a very simple function. Very simple formula for this function. Almost looks like almost too simple, right? But that is a function formula. Is that a linear function? So can you put it into this form, the mx plus b form? So can you write it as something times x plus the y-intercept? Is that possible? Arthur, you're saying no, okay? You're being a little bit pessimistic here, though, okay? What's your, why do you say no, though?
I just don't think there's enough in the actual expression.
So there's not enough there now, okay? But let's see if we can put enough there, all right? So what's missing? The mx, right, okay? You do not have the mx term, correct, okay? Is there a way that we can create that mx term, though, all right, and still not change the value of this formula? 0x, that's right, okay? So you can write that as 0 times x, right? And then the minus 5, okay? So, yes, this is a linear function, all right? The m value is 0. There's no restriction that the m value cannot be 0, okay? This is called, by the way, this formula, this is called a constant function because the output is always the same. The output is always constant. It's always minus 5. No matter what input you use here, no matter what x value you use, you always get an output of minus 5. See, no matter what input we use, the output always comes out to be minus 5, okay? That is still a function, all right? So some people think, oh, that's not a function because you're repeating the y value here. Remember, that's not a problem. It's repeating the x value with different y values that creates the issue. So, yes, this is a function. It's just a strange function or a very simple function in that it's the output is always the same, okay? Output is always minus 5. What about f? So what do you think? So this is a linear function because we can write it in that mx plus b format, okay? What about f? So if I were able to graph this, and well, I am able to graph it, but I'm not going to. If we graph this one, would the graph be a straight line? Okay. The answer here is no, all right. And the problem here is the square root of x, okay? You have x underneath that square root underneath that radical, and you're just not going to have that in linear function formulas, all right? In linear function formulas, you have x to the first power. M times x is m times x to the first power. So you're not going to have things like square root of x, okay? Or you're not going to have x in a denominator like this in a linear function, okay? X underneath the radical will not happen in a linear function. Now that I'm glad I have this example here, though, so I made these notes out with some care at some point when I made these notes out, okay? What about the domain of the, because we got to review domain here. So what about the domain of this function, square root of x plus 3, all right? That is remember, that is the other problem situation when you have a function formula, right? Because we cannot take square root of what kind of numbers? Negative. So we have to make sure whatever value we plug in for x here, right? We have to make sure it's not going to make the x plus 3 negative. In other words, x plus 3 always has to come out to be bigger than or equal to 0. And if x plus 3 is bigger than or equal to 0, then how big does x have to be? Bigger than or equal to what? Not 3, but negative 3, okay? Just add minus 3 to both sides of that inequality, okay? So we get x is bigger than or equal to minus 3. That is the domain, okay? That is the domain. X is bigger than or equal to minus 3, okay? That's the domain for this function, which is not all real numbers, okay? So there's another clue. That's only real numbers bigger than or equal to minus 3. So that's another clue that not going to be a linear function, right? Domain for linear function will be, in general, all real numbers. What about g now? Does that count as a linear function? Still has a square root in it, but there's a big difference here because in this formula, x is not in the square root, right? It's just the number 3 that's in the square root. So can we fit that into the, or is that already in the mx plus b format? Yes, it is. What's the m here? 1, right. The m here is 1, and the b value is what? Square root of 3, right? So this does count, g there does count as a linear function. So when you graph this, you're going to get a straight line, okay? Its y-intercept will be at the square root of 3, which is about 1.7, okay? So it's going to cross the y-axis at about 1.7. Finally, the last one here, could that possibly be a linear function? Notice I didn't give you specific values for m and b, but if you plug in a specific number for m and a specific value for b, can that be a linear function? No, because what's the issue there? X is squared, right? Yeah, so in a linear function, right, x will not be squared, right? X is just, as I mentioned before, x is just going to be raised to the first power in a linear function. We're going to study this type of function, okay? It's just slightly more complicated than a linear function and gives you just a slightly more complicated curve, all right? But this is not, when you graph functions like this, you will not get a straight line, okay? Not going to get a straight line out of that. All right, we got to do the same thing now here with, so this is not a linear function, okay? We're going to do the same thing now with tables. So when you're looking at a table, you have to rely on that third property. You have to rely on that third property. Remember that property said, that third property said what? When the x, or when the input changes by a steady amount, the output is also going to, when the input increases by a steady amount, the output is going to change either up or down by a steady amount also. So if you're looking at a table, that's what you want to look for, is steady change in the output. Steady change in the output. If that is the case, then you're going to have a linear function. All right. I don't know what the formula looks like for that linear function. Well, I know it's going to be mx plus b, okay, but I don't know what the m is yet. I don't want to know what the b is yet. All right, so what about a there? Is that going to be a linear function? So look, here we have the x increasing by a steady amount in this table, right? X is always increasing by what? 5, right? Okay, so x is going up by a steady amount. So we just have to check to see if y is also changing by a steady amount. Let's see. How is y changing here? By 2, right? Okay, is that right? Each time y is increasing by 2. So you see, each time, the way the table is made, that's convenient for us, right? X is always going up by 5, and y is also changing by a steady amount. It's always changing by 2, right? So that's it. Okay, that counts as a linear function. What about b now? So let's check the x. The x is going up by a steady amount, right? That's always increasing. It looks like 2 there. No, that's 3, right? So x here is always increasing by 3, right? So what about y? Is that changing by a steady amount? Let's see. First it goes up by 2, right? And then 3, and then 5, right? So there's definitely a pattern there to the changes in the y, right? But it's not steady, okay? Right? It's not steady. So we could extend this table, and we could figure out what the matching output is, right? When x goes up to 12, it looks like y is going to go up to 26, right? This change would be 7. So there's a nice pattern here, but it's not a linear function pattern, okay? Because in a linear function, the change in y would be simpler than this, okay? In a linear function, the y would have to change always by a steady amount, okay? But it's not changing always by a steady amount, okay? All right? In fact, y is going up by larger and larger amounts, right? Okay, as x increases by a steady amount there. So b is a nice function, okay? Might have lots of useful purposes, but not going to be not going to be a linear function, okay? C is kind of a trick question, but we've already seen an example like this one. All right, so let's look at this table. X here, the way the table is made, X is always increasing by what there? 1, okay? So we've got X there increasing by 1, and what's happening to Y? What's the change in Y here? 0, right, okay? Notice your matching outputs are changing by 0. That is a steady change, okay? That's a steady change of 0, all right? Okay, so that does count as a linear function, all right? So steady change of 0 is still a change, okay, for our purposes. So C there is a linear function. This is another example, just like we saw earlier, of what's called a constant function, because the output is always constant. The output here is, no matter what the input is, right, the output is always the same. The output is 11. Let's see what happens in D. That's a trick question. No. Okay. Why, Kevin? Yeah, what's wrong here? This table is not even a function, Kevin, right? Okay. Why? Yeah, so how are we going to write that on our test? If you have a table like this, and I ask you, is that a function, and explain why or why not, you said, I would say, no, it's not a function, but why not? Yeah, that's right, because there is an input that has more than one matching output. That's right. Two, right? Okay, that input has two different matching outputs. So not only is this not a linear function, this is not a function. All right, so not even a function. So definitely not a linear function. Let's see, what about the last one? I don't remember why I put this one in here. Let's see. Yes, right, okay. So, right, again, we've got x increasing there by 1, right, each time. And the y value there is, what, changing by -3? Yeah, remember the change in y can be negative. Y is going down by 3. So, yeah, this counts as a linear function. Now, now I remember why I put this example in here. All right, we can write down the formula now. I claim we can write down the. Well, I'm sorry. All right, we can almost write down the formula. All right, but we do know for this function now. We do know what the slope or rate of change of this function is, okay? Slope or rate of change, those mean the same thing, all right? And we know for this linear function what the slope is, okay? Because remember, the slope is the change in the y when x is increasing by exactly 1. So it's the change in y when x increases by exactly 1. So here, right, x is increasing by exactly 1. What was the change in the y there? -3. So the slope for this linear function is -3. What's the b value here? You can also read this off of this table. What's the b value? What now? -3, right? Emiliano, how did you decide it was -3? That's right, because b is the y-intercept, right? We already discovered that, right? B is going to be the y-intercept, and the y-intercept is always the output that matches the input 0. So we just, by luck here, we have x equals 0 in this table. So there's the output that matches the input 0, right? That is -3. So the b value for this function is, we know how now, is -3, okay? What is the, let's look at c here. This was also a linear function, right? What's the slope for this linear function? The slope, right? So that is the amount that the, again, that's the amount the y changes when x increases by 1. When x increases by 1, so, see, here we have x increasing by 1, right? What is the change in the y when x increases by 1? 0. So the slope here is 0. It is possible to have slope 0. What's the y-intercept? What's the b value here for this linear function? Y'all just told me for this one, so what is it for this one? What? Huh? 11. Right. Okay. Right. No, I'm pointing at C here. All right. Yeah, because the input is at 0, right? When x is 0, the matching output is 11. Okay, so the y-intercept is 11, so you know the b value for this linear function is 11. This was not a linear function. This one is a linear function, so I know the b value there. It's what? That one's easy to read, right? What? What? -4, right? Okay. So the b value there is -4. But now this one is hard to figure out what the slope is, okay? Or this one is harder to figure out what the slope is, all right? Because we don't have the x increasing by 1, right? See, slope is the change in y when x increases by 1. It's the change in y when x increases by 1. Unfortunately, in this table, I have x increasing by what? 5, okay? I don't have x increasing by 1. So it's not so easy just to read off the slope for this linear function. Let me show you, though, how you can calculate this. It's really simple. So look, what did we have in this table for the change in the x? 5, right? Okay. So when x increased by 5, right? When x increased by 5, how much did y change by? 2. So all you have to do is take that 2, the amount that the y increased by, and divide it by the change in the x, okay? And that will give you the slope. So the slope here is 2/5, all right? See, if think of it this way, if y is increasing by 2 when x goes up by 5, all right, if y is increasing by 2 when x goes up by 5, that means when x goes up by 1, y is going to be increasing by 2/5, all right? When x goes up by 1, y will be increasing by 2/5. So your slope here is not 2, but 2/5. That idea there is actually kind of important, so I want to write this down. All right, here is a formula you can use to calculate the slope if you can't see it immediately. It's just take the change in the y value and divide it by the change in the x value, okay? Even if the change in the x value is not, even if the change in the x value is not 1, okay? Just take the change in y divided by the change in the x, and that will give you the correct slope for the line. We're going to use this formula a lot, okay? So you'll get plenty of chances to memorize this slope formula. We're going to see it in lots of different forms. Okay, I think we're going to have to stop here. Oh, I was going to have you graph these lines, but we'll come back and graph the lines next time. That's pretty straightforward, okay? Graphing. Because what makes that so easy, right, is when you're graphing a line, right, that's a very simple curve. So how many points do you need to plot to graph a line? Just 2, that's right, okay? 1's not enough, obviously, correct, okay? But if you have 2 points, it's easy then to plot the line, right? Because you just connect the 2 points with a straight line, okay? That's an axiom, that's a famous axiom from geometry that says there's only one straight line that connects, any 2 points, right? So if you have no 2 points on the line, then it's easy to graph the line, right? Okay, so we'll get to that next time. All right, so I want to stop there, and we'll take a break of about 5 minutes, and then we're going to come back, and we're going to look at some of the problems on the sample test, okay? Some of the problems on the sample test that refer to straight lines, all right? So we're going to get a chance here to maybe practice here a little bit of our knowledge of straight lines, okay? And maybe some other stuff as well.